I would like again to begin by thanking the Inamori Foundation and its founder for this prize and for the wonderful things it supports both in science and for the betterment of humanity. I'm very, very humble and grateful that the foundation finds me worthy of this great honor. And now I would like to tell you a little bit about my early life and career, a little bit about how the Sloan Digital Sky Survey got started, and a bit about what it has found about the universe. You saw in the introduction a picture of me with my father. I was born in 1938. My mother was a quite gifted artist, but who decided to give up art for raising me. I'm grateful for that as well, of course. My father was a geologist, and he led a team during World War II to find oil for looking at places where the Earth's gravity was slightly low, and that indicated that there might be a pocket of oil below because oil is much less dense than rock. We moved around a lot as a kid, so I didn't really have a home. We would stay in a place about a year or so as my father moved from place to place. Because of the war, he had to become an expert machinist to keep his equipment up, and he taught me that skill, and that has stayed with me since. He died when I was 12 years old, and he was basically my friend. I had few friends because we moved around a lot. My teacher, my mentor, everything, and so it was quite bad. But I was interested in astronomy from the very beginning, really for as long as I can remember. I learned to read when I was fairly young, and the first book that I really remember, and certainly my favorite book, was a book called The Stars for Sam, which was written by a man, Maxwell Reed, for his nephew, a child. And he wrote a series of science books for children, and this book was published in 1938, the year I was born, and was a sort of major formative thing in my life. Once I read this book, I never really deviated very far from wanting to be an astronomer. I didn't have very much idea what astronomers actually did, of course, but I was interested in the stars, and I wanted to study the stars, and that stayed with me the rest of my life. My father was a geologist, but he was very interested in astronomy, and now he had a child to teach things, and so he had always wanted to build telescopes, and so we built little telescopes when I was a kid. And I was so taken by the subject that after he died, I continued to build telescopes. And when I was in high school in Texas, long after he died, I built this photographic telescope, which actually resulted in my first astronomical publications in about 1965. And so here is a picture of the telescope, there it is, the 8-inch telescope, and a photograph. It was an electronic drive, as the introduction said, and also had a camera. So I was able to take astronomical photographs, and I became very, very interested at that point in astronomical imaging and the state of the art in astronomical imaging. I was an undergraduate at Rice Institute in Texas. I majored in mathematics and physics. Did some research actually very early. This was in 1965. Computers were just coming along, were not used. They were used in business a fair amount, but were just beginning to be used in science. And I was lucky enough to get in at the very beginning of that and learned how to do scientific programming when I was yet an undergraduate. Graduate school, I went to Caltech in California. I wanted to do general relativity and went to Caltech to work with a man who died the summer before I arrived. So I was not able to work in general relativity, but became interested then in, I was still interested in observational astronomy, and was very interested in the universe in the large, and I became very interested in observational cosmology. That is, the cosmology is the subject of treating the universe as a whole, as an object, to try to understand how it expands and so on. I was very interested in Einstein and general relativity, and I did some work in gravitational lensing, which was quite important at the time. And also, about the time I was finishing graduate school, quasars were discovered. And it was thought that they were very, very far away. And I did some work with a fellow graduate student, Bruce Peterson, to look at the gas between the galaxies and the universe far away. And we were able to come up with an idea that you should or should not see this stuff, depending on exactly how it worked. And there came to be something called the Gunn-Peterson effect, which was not discovered for many, many years. And actually, it was the final thing was discovered by the SDSS much later, and we'll talk a little bit about that when we get there. While I was there, I continued to build instruments, both optical and electronics. And I became very interested in a particular aspect of cosmology, of the science of the universe, and that is how galaxies are distributed in space. Galaxies, as all things in the universe, gravitate, and so they pull on one another by gravity. And as a result, their distribution in space is not completely random, because where there are a few more, the gravity is a little higher, they pull and become even more. And so these clusters are one of the largest structures that we see in the universe. I did my thesis on this topic, and investigating something called the correlation function that says how much more probable, if you have a galaxy, is it that you have a neighbor than it would be if the galaxies were just strewn in space completely randomly. And this tells us a great deal about how the universe evolves and about how gravitation works on these very large scales. This is a picture, just a 2D picture, made from photographic data. This is of the southern sky, actually. So each dot in this picture is a galaxy. And you can see that the galaxies are not distributed randomly on the sky. You see clusters, you see groups, you see many, many things. All of this is the result of gravitation pulling galaxies together. This is simply a two-dimensional picture. If you add depth, and this was an early survey done at Harvard, the Harvard-Smithsonian survey, the depths are, the distances are color-coded, and so you can see that there's really very, very strong structure in 3 dimensions. And so I became very interested in making surveys that would do a better job. The statistics of galaxies in space, in order to do this well, is to do any statistical problem. If you're doing a sociological statistical problem, you have to have very large and very carefully chosen samples. And it's the same in doing statistical astronomy. Many astronomers spend their lives studying a few objects, a class of objects, sometimes only one object. And this is enormously important for giving us the depth of understanding in single things. But my emphasis was a little different. I wanted to study whole populations, to study the statistics, and to try to figure out, in the large, how the universe came to be the way it is today. This requires very, very large telescopes with very large fields, because if you want a big sample, you have to study a lot of sky, and that means you have to look at it, a lot of it at once. So you need very sort of wide field lenses in astronomy. And this is basically the story of my career for a very long time. 60 years ago, there wasn't very much in the way of surveys. There were small survey telescopes that made maps, partly for navigational reasons, partly just to find the locations of stars in the sky. But these surveys did not record very faint objects, and they didn't really allow quantitative interpretations of things, because it was just photography. Photography is beautiful, of course, to take pretty pictures, but it's very difficult to make quantitative measurements from. So all this changed actually began a long time ago, just as OLEDs began a long time ago before today. A fellow called Bernard Schmidt, who was a rather crazy Estonian optician, invented a camera that would make very, very wide fields in the sky, called the Schmidt camera or the Schmidt telescope. And there was a remarkable fellow called Fritz Zwicky at Caltech who realized the enormous impact of this on doing surveys. And Zwicky was one of the people who really pushed the idea of doing surveys. And he pushed very hard for a project to image the whole northern sky. And this was done with a big Schmidt camera that he persuaded people to build. And it ended in 1957. It resulted in a product called the Palomar Observatory Sky Survey, or the POSS, which was photographs in red and blue light over the whole sky. He was a very interesting fellow. He's really one of my heroes in life. This is a picture of him, I think, in a kind of typical pose, and with the 18-inch Schmidt that he built. Zwicky didn't like astronomers very much. He thought all of his colleagues were fools, and there are many, many wonderful quotes from Zwicky, and this is, I think, one of the best of them. Astronomers are spherical bastards. No matter how you look at them, they are just bastards. But he is one of my heroes because of the emphasis on surveys. He also did really marvelous things early on. He predicted the supernova phenomenon. He predicted neutron stars. He knew that there was dark matter long before anyone else did. This is a picture of the 48-inch Schmidt that made the Palomar Sky Survey. So I want to step aside a minute from this general stream and talk about something which is very important for surveys. We have to have pictures, of course, to know where things are, but pictures don't tell us how far away things are. And in order to find out how far away things are, we need another tool. And the tool that we use is called spectroscopy. So let me spend just a few minutes talking about spectroscopy. One of the phenomena of light, of any kind of wave thing, is something called the Doppler shift. So if I have a galaxy that's moving, a star that's moving, anything that's moving, it compresses the waves, the light waves in front of it in the way it's going. So the object is moving this way. You can see that this sphere of light was emitted when the object was back here, but the object has moved, and so the waves are compressed in the direction the object is moving, and they are stretched in the way the object is moving from. So if something is moving away from you, the wavelength of the light is longer, that's called, and its longer wavelength of light is red, that's called the red shift, and if it's moving towards you, the waves get closer together and moves to the blue, and that's called the blue shift. And we use this phenomenon to measure distances. The universe is expanding. We've known that for a long time. And what that means is that distant objects are moving away from us at very, very large speed. And the further away an object is, the faster it's moving. And there is a very simple formula that just says that the distance is some magic constant called the Hubble constant times the speed. And so if the speed is twice, the distance is twice. And that makes it very easy to sort things out in the universe. How do we do this? How do we measure the wavelength? Well, this is where spectroscopy comes in. We build an instrument which splits light into not just red, blue, and green, but into thousands of colors. And these individual colors tell us many, many things about the object, as we'll see. It makes a thing called a spectrum. The spectrum is just how much light there is at a given color of one of these thousands of colors. So the spectra of galaxies look like this. So here are three galaxies which are quite similar. This is the blue end of the spectrum, so this is blue light, that's red light. You can see that the objects at the top have a lot more red light. The objects at the bottom have a lot more blue light. You see several other things in here. Here you see a strong feature. That strong feature is repeated here, and it's repeated here, but it's at a slightly different place. That feature is the result of the absorption of light by calcium atoms. Well, that tells us something interesting, because it says that this galaxy, hundreds of millions of light years away, has calcium in it, the same calcium that we see on Earth. That feature is magnesium. That feature is sodium. So we see from these spectra what the object is made of. The fact that this one is shifted farther to the red than this means that it is receding from us more rapidly. That number is given by this redshift number here. We'll get back to that later. So this object is relatively nearby. This object is moving faster and is farther away. This object is moving faster yet and is even farther away. And so from this, we see what the objects are made out of, but we see more. This object is blue. This object is red. The blue comes from very young stars that were made only a few million years ago. This object has no stars that were made only a few million years ago. So these spectra tell us an enormous amount about the chemistry, about the history, and in fact, about the motion of these objects. So it tells us what the object is made of, how fast it's receding, and therefore how far away it is if it's out in the expanding universe, what are the temperatures of it, and also, if you think about it, the stars in these galaxies are in orbit about the center, and so some of them are approaching and some of them are receding. The result of that, there we go. The result of that is that if things are moving rapidly, these lines are broad, and if they're moving slowly, they're narrow. So we see not only how far away, how fast the thing is moving, but how fast things in it are moving with respect to one another. So we come back to surveys and how you do them. Photography it makes beautiful pictures, but it's not a quantitative method. And there was a lot of work, this kind of parallels what Dr. Tang told us about light emission. Astronomers don't need light emission. We need devices that record light. And there has been an enormous amount of work kind of paralleling, in a way, the work that he talked to you about light emission. Certainly photography would not have done this. We could not do a better survey with photography. We need new detectors. So in the 1970s, when I was at Caltech, Jim Westphal and I started working with a technology called CCDs that were developed at Bell Labs and that NASA were very interested in for space missions. We proposed and won a contract from NASA to build the camera, the first camera, for what was called just called Space Telescope then, that is now called Hubble. CCDs are very efficient, but at first, just as with the displays that Dr. Tang talked about, they were just too small. We needed bigger things. With the small CCDs, we built a camera called 4-shooter. This is a picture of the 4-shooter team on the 200-inch telescope at Palomar. The instrument is this big black thing in the background that you can hardly see. Here is Jim Westphal, my co-collaborator on the Space Telescope, and a small team of people, of really excellent people, who built the instrument. So we needed something bigger. So in 1986, a fellow called Morley Blount that we had been working with at Texas Instruments moved to another company called Tektronix that was interested in making very big CCDs for things that didn't work out. But never mind, they made big CCDs. And Morley showed us this is a single silicon wafer, 100 millimeters in diameter, with a single device on it. And when I saw this, I knew that here was a way to do this wonderful survey that I had been wanting to do for most of my career. So let's build a camera, put a lot of these on one focal plane, and go from there. So this was the beginnings of the Sloan Digital Sky Survey. So I worked for a couple of years designing these things. I needed to design a new kind of telescope, actually, to use it. A big focal plane with many of these, many filters to obtain color data to get temperatures over as big a range as possible, and also to work on digital storage of the data, because if we had a lot of data and it was not available in digital form, it would not be very useful. But the survey would also not be very limited without spectra. But this big CCD was also a perfect device to serve as a detector for spectrographs. But if we want to do several objects at once, Why would we want to do several objects at once? Well, when you break the light into all these thousands of colors, each color becomes very, very faint. And so it takes a very, very long exposure in order to record this spectrum. A picture, there are only a few colors, and the colors are still pretty bright, and it doesn't take very long. So it takes much longer to get spectra. Just as an illustration, to do what Sloan did, suppose you wanted to take the spectra one by one with a telescope. The exposures are of the order of an hour each. 1 million galaxies, 1 hour, that's 1 million hours. At a very good site, astronomical site, there are about 1,000 dark clear hours per year, and with no overhead at all, but there's always overhead just making things work, it takes 1,000 years to take 1 million spectra. And I don't think any of us were quite ready to wait 1,000 years. But if you can do 500 at once, it only takes 2 years to do this. So the planning began for what became the SDSS. We had just joined an observatory, a new observatory building in New Mexico. The site seemed quite good for this, and we rather slowly and with difficulty obtained funding for this with a very large gift from the beginning from a fellow on the board at Princeton. And so eventually, the people involved in the Sloan survey were these, and I would like to bring your attention to this, a very, very large lot of work in the Sky Survey was done by the Japan SDSS promotion group. So Japan has been our colleague in this for a very long time. Why did it start then? Well, it really couldn't have started earlier because the technology simply wasn't there. We had to have the big CCDs. We had to have high-efficiency optical fibers. I'll say more about fibers in a minute. That's how we get many spectra at once. And cheap and readily available computing to handle all these things. So the goals of the survey were to image the whole sky as 40,000 square degrees, and to look up out of the Milky Way galaxy into the sort of clear part of the sky was to image the 10,000 degrees in the north, to classify and measure all the objects we could take pictures of, which was many more than we could take spectra of, about 200 million, to measure the redshift distances to the brightest million galaxies and the brightest 100,000 quasars, and to put this data together in a database that people could use. This picture you've seen before. This is just the Princeton team, but there were many, many institutions. Here is me and my wife, Jill, who played a very important role in the software in this project, a couple of our Japanese colleagues, and many others sitting in this room. So this is the site. The new survey telescope is here. You've seen pictures of it before. A nice picture taken at sunset. This is a picture of the instruments at the telescope. The two big green things are the spectrograph, and the camera, which had 30 of these big CCDs, is in the center. This is a picture of the focal plane. There were 30 of these things, and they were arranged from red, green, two infrared, an ultraviolet filter and two infrared filters, so that we got, as a star went through this, we got data in all 5 colors in about 5 minutes. This is the distribution in the spectrum of the light from the ultraviolet, green, red, infrared, and farther infrared, and we recorded all of those basically simultaneously. Here is spectra. We did this by making a large aluminum plate, drilling holes at precisely the locations of galaxies that we learned from the imaging, plugging optical fibers in. The optical fibers come down, make the spectra, and go to the CCDs. You've seen this picture before. These are representative spectra from the survey. This is the sky that we covered, and you can see the dark is the main northern area. The green is a survey to look not at galaxies, but at stars. This was the data release at the end of the first phase of the survey, 8,000 square degrees, not quite 10,000, but we did the 10,000 in the next year. Photometry for several hundred million objects. Spectroscopy over 7,000 square degrees, 1.2 million spectra, and a lot of spectra of stars. So this is a kind of step through the survey. This is a picture with these bright things are put in by hand. They are the bright stars in the sky, just to sort of orient you on the sky. And what we're going to do is just zoom in, but we could zoom in to anywhere in this area, just as we're going to zoom in here. So we get closer. You can begin to see in the center maybe what we're heading for. This is called the Whirlpool Galaxy. So from that large area over the sky, one can focus and zoom in on any object you want in that large area. And there were many, many lovely objects we took pictures of. This is a picture of a globular cluster of a galaxy that is exploding currently. This stuff in the middle is not just a mist. It's gas being blown out of the center from a major explosion in the center. A beautiful spiral galaxy. A galaxy that has just suffered a collision with another galaxy. Galaxies don't always keep to themselves. They interact in very nasty ways with their neighbors. This is the nearest galaxy to us. This is Andromeda, the Andromeda spiral. And what I want to draw your attention to is this area. We're going to zoom in on it. This is just in one nearby galaxy. So we're getting closer. We're looking at a star formation region. This is gas, which is excited by hot stars in this galaxy. We come in. We also step way out in the universe. These are nearby clusters of galaxies. This is one in Coma, Hercules. And even farther, this group here is a group of galaxies at a redshift of about 0.3. That means about 30% of the way back toward the Big Bang in the system. And this is sort of at the limit. In this was just a single pass. We also did part of the sky, in which we did many, many times, so that we could add the pictures together. And you can barely see right in here anything, but clearly when we stack things together and make very long exposures, this is a cluster at about a redshift of 1, when the universe was about half its present age and half its present size. Lots of beautiful things in the Milky Way galaxy. These are all gas clouds in the galaxy in lovely colors. Now, this is the sort of 3D distribution. You saw the movie at the beginning. This is distance. So we're looking, this is just a thin slice of sky, looking at how the galaxies are arranged. And you can see that there are filaments, there are voids, there are clusters. It's a very complicated structure. How did this come to pass? Well, in 2001, this rocket was launched, which had a satellite, which made a map of the microwave sky. This is called the Cosmic Microwave Background, the WMAP sky. The real distribution of this, it's almost completely uniform. The brightest things in here are about a part in 100,000 brighter than the coolest things here. But it is these little ripples in the early universe that made the structure we see. So we now know, and I really don't have time to go into how we know these things. The universe began 13.6 billion years ago. The universe is full of energy. And Einstein tells us that energy and mass are the same thing, in a way. And the things that we know about, protons and neutrons and electrons, is only about 4% of this. 25% is dark matter, and the other 70% is some dark energy that we don't quite understand. So let me say, if I go to a place where there is a very slight bump in the mass distribution, and follow it, what happens is this. This is a bump in everything, in the ordinary matter and the dark matter. There's a lot of pressure in the early universe. It's very hot. And that pressure pushes the ordinary matter out, but the dark matter doesn't feel this pressure. So you see the ordinary matter, which is only a small part, going out, and the universe is cooling at the same time, and it becomes cold. And what's left is around every place that there was a bump, a hill, in the early universe, there is an extra distribution of matter. Can we find that in this? Yes. If we count galaxies going out from the distance from a big galaxy, this is the correlation function that we talked about, you see that it drops off very smoothly, but there's a hump. So there are slightly too many galaxies in this ring. And this tells us that we understand pretty well what is happening in the early universe. Something else the Sloan did, because we had spectra of 1 million galaxies, we could easily look at their distributions. I don't have time to go into this in any detail, but this is colors, brightnesses, sizes, all of these things we can look at and look at the relations between. Let me call your attention to this picture. This is color versus brightness. These are bright galaxies. These are red galaxies, and let's look at that in a little more detail. So what we found was that there was a red sequence. These are the galaxies that we looked at that were red and not forming many stars, red and dead, they're called. There is a kind of green valley that separates these, and these are the blue things that are making stars like mad, even today. And so we want to understand how this developed from the microwave background and also how it developed and what we saw. We also studied the chemistry of galaxies. Stars make all of the things we are, the carbon, the nitrogen, potassium, all of these things are made in stars. And galaxies hang on to that gas when the stars explode. The stars explode, and that's how these things get out. Big galaxies, because they have high gravity, can hang on to this stuff. Little galaxies, these are big galaxies, these are little galaxies, are not so good at hanging on to it. And so there is a strong range of chemistry with mass. So the results of the SDSS, I think the ones I'm proudest of are these. We study gravitational lensing. Gravitating objects bend light. And so you can study this, you can use this to detect directly masses in the universe, because you can look at how they bend light together. The baryon acoustic oscillations are what I showed you before, this pushing out of the ordinary matter. The properties of galaxies we saw. But also in the solar system, we discovered thousands of asteroids and looked at families of asteroids, chemical families, orbital families. We didn't really set out to explore the solar system, but we did. We found brown dwarf stars. These are objects which are between stars and planets. They don't burn thermonuclear fuel, and was thought for a very long time that they existed, and they were discovered actually before Sloan, but we found many, many of them and studied their properties. And of course, the large-scale structure of the universe. So the impact of this, as of the end of last summer, there were 10,000 scientific papers which used SDSS data. These papers were cited nearly 500,000 times. There were 1,000 papers with more than 100 citations, and 7 among the 100 most cited papers of all time. But it wasn't all we did. So there was also a very important legacy, I think, for the science. We insisted from the very beginning that the data would be made public very quickly, and we succeeded in doing that. And this resulted in the really natural growth of collaborations over the world using our data, both within the collaboration and without. And this openness is something that I hope it actually has become part of the sort of scientific sociology of astronomy, and it appears to be being a model for new projects. There was also citizen science. There was something called the Galaxy Zoo. We published a lot of pictures and asked the public to help us classify these things. We didn't even have any idea whether it would work, but within a day of the publication of this, we had 70,000 entries and over 150,000 people did this, worked on this as we went on. So that's sort of where we are and have been. The SDSS was finished some time ago. What do we want to do next? Well, it's very important to know that when we look out into the universe, we also look back in time. And so the universe is its own history book. If we can look out far enough, go faint enough to objects far away, we can study what the universe was like 1 billion years ago, 2 billion years ago, 10 billion years ago. And so the next step, I think, is to go out and be very faint. We know today that the universe actually is in its dotage, it's dying. This is a graph of the star formation in the universe, which is sort of the activity of things. This is a look back time, so this is now. If we look back 10 billion years, 10 times as many stars per unit time were being born as are born today. So the universe was an incredibly active, noisy place compared to the rather quiet times of today. So we'd like to do a survey like SDSS, but with much bigger telescopes, to go much fainter, to study things far enough away that we can read this history. And it's happening. Japan is making it happen. There's a beautiful camera with 114 even bigger CCDs than we used, called Hyper Supreme Cam. Satoshi Miyazaki, who I hope is in the audience and is there, oversaw the building of this. This is a photograph taken at the commissioning of this instrument at the Subaru telescope. And the imaging part of the survey is underway and more than half complete. These are pictures of the instrument. It's very big. As you can see, here is a human being by comparison. This is the team that actually built the camera, and this is the focal plane with 114 CCDs in it. This is a picture that the telescope made. I think even on this screen it doesn't do justice, but you can see that there are very, very, very many galaxies. The galaxies almost overlap. So the faintest of these galaxies came at a time when the universe was only about 1/5 its present size and 1/5 of its present age. What about spectroscopy? Well, we have to have a spectroscopic component. We're working very hard on a spectrograph for Subaru that, again, will use fibers, this time many, many more fibers, 2,400 fibers, and it will reach ordinary galaxies out to the place where the universe was doing all of this really active stuff. And this instrument has been my focus for the past some years. I said the universe makes its own history book. It's hard to read because you have to go very faint. You have to have very sensitive instruments and go very deep in order for it to work. And we're doing our best to try to read this book. We, of course, I can't say that we're completely ignorant of it because surveys, small surveys, lots of work on smaller numbers of objects is going forward, of course, all over the world, but nothing like the size of the SDSS and nothing like the size of these surveys that we're talking about that Subaru is doing. So I would like to express my thanks not only to the Inamori Foundation for this enormous honor here, but also for the privilege of working with a very large and excellent group of Japanese astronomers since SDSS days. And now, you know, I was part of running the SDSS, but they have taken over and are doing a very much better job with very big telescopes. I should also say, and I did not say really sufficiently, that you saw the list of institutions for the SDSS. I was project scientist for the SDSS, but the work I did was 1%, some tiny fraction. All of that work was done by my colleagues at these institutions, and especially wonderful for me was that the work was mostly done by my younger colleagues. So we old guys and gals who ran the survey, and we did a pretty good job, but the science was mostly done by the young colleagues, and they did a wonderful job. And that continues in the projects today, and I am enormously proud of that. I was kind of the father of SDSS, but it was my children who did the work. So thank you all, and thanks especially to the Inamori Foundation.
ありがとうございました。Thank you very much, Dr. Gunn. Please move to center of the stage to receive flowers. ジェームズ・ガン博士、ありがとうございました。